Dimitri. Hi there. For this session, we will be discussing about precipitation and precipitation techniques. First, let's define precipitation. Precipitation is a process which involves combining soluble antigen with soluble antibody to produce insoluble complexes that are visible even to the naked eye. In 1897, an Australian pathologist, Rudolf Krauss, introduced the fluid precipitin test. He took bacterial filtrates, which he injected into rabbits. He later on took the serum containing the antibodies, or the precipitin, and incubated it with the bacterial filtrates, or the antigen, and got a precipitation reaction. So precipitation reaction in the precipitin test conducted by Rudolf Krauss signifies the presence of antigen-antibody complexes. For precipitation to occur, basic requirements must first be met. Number 1, both antigens and antibodies must be multivalent. So for antigens must have multiple binding sites, and for antibodies involved for precipitation have at least 2 binding sites, so that would be IgG. Another requirement is both antigens and antibodies concentration must be optimum for the system. So their concentration must be approximately equal to each other, or both concentration must be in the zone of equivalence to demonstrate precipitation. In this animation, we can find the reaction of multivalent antigens and antibodies. So the blue structures are the antigens with multiple binding sites, and for the antibody, we have here IgM. So if we are dealing with multivalent antigens and antibodies, there will be a visible reaction. If we are dealing with univalent antigen and bivalent antibodies, there will be immune complexes formed. However, there will be no lattice formation. So this is an invisible reaction. Now, as a recap, for formation of lattice at varying antigen-antibody ratios, we have here the graph which shows the increasing antigen concentration at the x-axis and the concentration of antigen-antibody complexes at the y-axis. Now, for the illustration, you can find there 3 zones. So the first is the pro-zone phenomenon, wherein there is excess in antibody concentration. So the excess in antibody concentration will result to saturation of antibodies to the binding sites of the antigens, thereby inhibiting the formation of cross-linkages among the immune complexes. So this will result to false negative reaction. At the zone of equivalence, the concentration of antigens and antibodies are approximately equal to each other. So this will result to cross-linkages of immune complexes, thereby allowing lattice formation. So the result is precipitation. In the post-zone phenomenon, there is excess in antigen. Excess in antigen will usually obscure the immune complexes formed, thereby resulting to false negative reaction. To overcome pro-zone phenomenon, we can dilute the patient sample to adjust the concentration of the patient's antibody. To overcome the post-zone phenomenon, patient is usually requested for another set of testing at least a week after to allow antibody production to achieve its detectable levels. for antigen-antibody binding, there are some principles that are needed to be considered. Okay, so number one, we have affinity. Affinity refers to the initial force of attraction that exists between a single Fab site on an antibody molecule and a single epitope or antigenic determinant site on the corresponding antigen. Now, the forces involved in antigen-antibody binding are non-covalent. So, it is still possible that one epitope bound to one paratope will be dissociated because they are based on non-covalent bond. So, therefore, the reaction is reversible. Now, these forces are generally only effective over short distances. So, examples of these forces are the following. First, we have electrostatic or ionic attraction. So, this attraction occurs between oppositely charged particles. So, for example, we have cations or positively charged particles will be attracted with anions or negatively charged particles. Number two is hydrogen bonding. So for hydrogen bonding, this involves an attraction between polar molecules that have a slight charge separation and in which the positive charge resides on a hydrogen atom. So hydrogen has the capacity to bind with other chemical elements such as oxygen. So oxygen binding with hydrogen, or we have nitrogen binding with hydrogen, or both. We have oxygen bound to hydrogen and hydrogen bound to nitrogen. So that is hydrogen bonding. Next is hydrophobic bonds. So for hydrophobic bonds or hydrophobic interaction, this occurs between nonpolar molecules that associate with one another and exclude molecules of water as they do so. So in this structure of our antigens and antibodies, there are hydrophobic surfaces on their molecules. So once the antigen is specific for the antibody in the system, they tend to move toward each other. So as they move towards each other, there will be conformational changes in their molecules. And these conformational changes will expose the hydrophobic surfaces of these molecules. So in the illustration or animation, we have there one of the properties of our antibodies, and that is specificity. So specificity refers to the ability of our antibodies to distinguish structural differences in epitopes. So basically, the antibody which is produced to, for example, this round epitope will only bind with the round epitopes and not with other kinds of epitopes or shapes. However, there are some instances wherein cross-reaction or cross-reactivity happens. So when you say cross-reactivity, this occurs when an antibody binds to different but structurally similar epitope. Antibodies are also capable of reacting with antigens that are structurally similar to the original antigen that induced antibody production. The more the cross-reacting antigen resembles the original antigen, the stronger the bond will be between the antigen and the binding site. On the illustration, however, you will find there that if the epitope and the binding site have a perfect lock and key relationship, as for example in the case with the original antigen, the affinity will be maximal because there is a very close fit. Another, we have avidity. Avidity refers to the overall strength of attachment of an antibody to an antigen. Now, avidity involves the strength with which a multivalent antibody binds with a multivalent antigen, and it is a measure of the overall stability of an antigen-antibody complex. So avidity represents the sum of all the attractive forces between an antigen and an antibody. So once binding has occurred, it is the force that keeps the molecules together. So a high avidity can compensate for a low affinity. The stability of the antigen-antibody complex is essential to detecting the presence of an unknown, whether it is an antigen or an antibody. Next, we have the law of mass action. All antigen-antibody binding is reversible and is governed by the law of mass action. Now, this law states that free reactants such as antigens and antibodies are in equilibrium with bound reactants. So the AG, or the antigen-antibody there represents the antibody-antigen complexes. The equilibrium constant represents the difference in the rates of the forward and reverse reactions according to the following equation. So we have antigen and antibody with the rate constant for the forward reaction, or K sub 1, will result to antigen-antibody complexes. And antigen-antibody complexes with the rate constant for the reverse reaction will dissociate into antigens and antibodies. The equilibrium constant is thus K, or equilibrium constant, equals the rate constant for forward reaction, or K sub 1, over the rate constant for the reverse reaction, or K sub 2, which is equals to the immune complexes or antigen-antibody complexes over antibody concentration times antigen concentration. This constant can be seen as a measure of the goodness of fit. So its value depends on the strength of binding between antibody and antigen. So as the strength of binding or avidity increases, the tendency of the antigen-antibody complexes to dissociate decreases, and the value of K sub 2 decreases. This increases the value of K sub 1. Now, the higher the value of K, or equilibrium constant, the larger the amount of antigen-antibody complex and the more visible or easily detectable the reaction is. The ideal condition in the clinical lab would be to have an antibody with a high affinity or initial force of attraction, as well as a high avidity or strength of binding. The higher the values are for both of these, and the more antigen-antibody complexes that are formed, the more sensitive the test will be. Next are the factors affecting the degree of precipitate formation. So number 1, we have reaction time. Basically, the longer the reaction or the incubation time, the better the precipitate formation. Next is the temperature. For the temperature, we have to consider the antibody class involved in the test. So if we are dealing with IgG, usually we incubate the mixture at 37 degrees Celsius. If we are dealing with IgM, we can perform the test at cold temperatures ranging from 4 degrees Celsius up to 27 degrees Celsius. Number 3 is mobility of reactants in solution. So in some cases, we need to apply movement to enhance the precipitation reaction, such as rotating the slide or rotating the reaction card to enhance the antigen-antibody complex formation. Number 4 is electrolyte concentration in solution. Generally, if electrolyte concentration is increased, this will hinder the reaction between antigens and antibodies. And number 5, we have pH of solution. So for optimum reaction, generally the pH is adjusted close to physiological pH, that is about 6.5 to 7.5 pH. For the measurement of precipitation in fluid phase, we can perform either turbidimetry or nephelometry. Turbidimetry measures the amount of light blocked by the particulates, so there is subsequent reduction in light intensity. While nephelometry measures the amount of light that is scattered at a particular angle from the incident beam as it passes through a suspension. The amount of light scattered is an index of the solution's concentration. So beginning with a constant amount of antibody, increasing amounts of antigen result in an increase in antigen-antibody complexes. Thus, the relationship between antigen concentration, as indicated by antigen-antibody complex formation, and light scattering approaches linearity. Now, to illustrate that, in turbidimetry, a detection device is placed in direct line with the incident light, collecting light after it has passed through the solution. It thus measures the reduction in light intensity due to reflection, absorption, or scatter. Scattering of light occurs in proportion to the size, shape, and concentration of molecules present in solution. In nephelometry, this measures the light scatter at angles ranging from 0 degrees to about 90 degrees. If a laser beam is used, light deflected only a few degrees from the original path can be measured. Although the sensitivity of turbidity has increased, nephelometry is more sensitive with a lower limit of detection of about 1 to 10 milligrams per liter. Nephelometry can be used to detect either antigen or antibody, but it is usually run with antibody as the reagent and the patient antigen as the unknown. Next is the passive immunodiffusion. In passive immunodiffusion, either antigen or antibody is allowed to diffuse in a gel medium and a precipitate is formed at the zone of equivalence. Now, the rate of diffusion in passive immunodiffusion is dependent on the following. Number 1, molecular size. So basically, if the molecules are small, they tend to move faster. So there will be increased rate of diffusion if the molecules of interest in the gel are small. Next is temperature. Okay, so for the temperature, this also has a connection with the antibody class that we are dealing with in the test system. So for IgG, we have to incubate the gel medium at 37 degrees Celsius to allow optimum reaction between antigens and antibodies. While for IgM, reaction can be observed at temperatures ranging from 4 degrees Celsius up to 27 degrees Celsius. For gel viscosity, always monitor the viscosity of the gel. Avoid using gel that is highly viscous because this will impede the movement of the molecules in the gel. Also, for the gel hydration, we have to make sure that the gel is well hydrated to allow the movement of the molecules inside the gel. If the gel is dry, this will impede or inhibit the movement of both antigens and antibodies. And the number 5, interactions with gel matrix. Keep in mind that molecules of interest may have different sizes and shapes. So we have to consider also their interaction with the gel matrix. If the gel matrix matrix has small areas for passing, then that will impede the movement of our molecules. So in that case, we need to use another type of medium to facilitate the movement of the molecules inside the gel. Next is the single passive immunodiffusion. So in single passive immunodiffusion, only one reactant is allowed to diffuse while the other is fixed in the gel. So if we are looking for the patient antigen, there must be the presence of specific antibodies which are already bound on the gel medium. So for example, we have one-dimensional single passive immunodiffusion such as the Oden technique, and then we have two-dimensional single passive immunodiffusion such as in radial immunodiffusion. So under the radial immunodiffusion, we have the endpoint method or the Mancini method and the kinetic method or the Fahey and McKelvey method. For the Oden technique, this was introduced by James Oden. So he was the first to use gels for precipitation reactions and pioneered the technique known as single diffusion. So in single diffusion, antibody was incorporated into agarose or agarose gel in a test tube. Then the antigen was layered on top. So patient sample must contain the specific antigen to our antibodies on the agarose gel. And as the antigen moved down into the gel, precipitation occurred and moved down the tube in proportion to the amount of antigen present. So basically, if we have antigen-antibody complexes formed, there will be precipitation. Next, we have two-dimensional single passive immunodiffusion. So in this one, this is a modification of the single diffusion technique. So antibody is uniformly distributed in the support gel, and then the antigen is applied to the well cut into the gel. So as the antigen diffuses out from the well, antigen-antibody combination occurs in changing proportions until the zone of equivalence is reached and a stable lattice network is formed in the gel. The area of the ring obtained is a measure of antigen concentration, and this can be compared to a standard curve obtained by using antigens of known concentration. So to understand the principle of radial immunodiffusion, let's focus first on the animation. Okay. So in this animation, uh, we have here the gel, okay, which serves as the medium. Okay, so in the gel, we have their fixed antibodies. And then at the center of the gel, we have the antigen well. Now, when you say well, that is just a cut or a hole in the gel. So this is where we place our patient sample. And if our patient sample contains the specific antigen against the antibodies present on the medium, then after some time, antigens from the patient sample will diffuse across the medium, and at the zone of equivalence, it will form precipitates. Okay, so here in radial immunodiffusion, precipitation is manifested as a precipitin ring. So usually, we get the diameter of the precipitin ring, and the area of the ring obtained is a measure of antigen concentration, and this can be compared to a standard curve obtained by using antigens of known concentration. So in this reaction, the area nearest to the antigen well has the highest antigen concentration, or it can be referred to as the post-zone area or post-zone phenomenon, wherein the area where we can find the precipitation or precipitin ring, this is the area of the zone of equivalence. So for the two methods of radial immunodiffusion, we have Fahey and McKelvey method, and we have the Mancini method. Mancini method is also known as the endpoint method because in this technique, antigen is allowed to diffuse to completion, and when the equivalence is reached, there is no further change in the ring diameter. So usually in the Mancini method or endpoint method, the reaction is read after 24 hours or within 24 hours to 72 hours. And then the square of the diameter is then directly proportional to the concentration of the antigen. And then a graph is obtained by plotting concentrations of standards on the x-axis versus the diameter squared on the y-axis, and the smooth curve is fit to the points. Another technique for radial immunodiffusion employed in the laboratory is the Fahey and McKelvey method, also known as the kinetic method. So in this method, it uses measurements which are taken before the point of equivalence is reached. So the diameter is proportional to the log of the concentration. So therefore, if the rate of diffusion is high, that means to say the concentration of the antigen is also high. A graph is drawn on semi-log paper by plotting the antigen concentration on the log axis and the diameter on the arithmetic axis. So readings are taken at about 18 hours. Now here are the following sources of error in radial immunodiffusion. We have overfilling or underfilling the wells, leaking the side of the wells when filling, spilling sample outside the wells, improper incubation time and temperature, and incorrect measurement. Now all of these factors will result to falsely increased or falsely decreased reading. Next is the double passive immunodiffusion. Okay, so when you say double passive, it means to say both antigens and antibodies are allowed to diffuse through the neutral gel matrix. So common example of a double passive immunodiffusion is the Auchterlonie technique. So in Auchterlonie technique, there is a formation of precipitin bands at approximately the point of equivalence between reacting antigens and antibodies, and these precipitin bands are perpendicular to the axis line between application points. The position of the precipitin bands will appear between the reactants in a position relative to each concentration. So for example, during antibody it says the precipitin bands will be formed near the antigen well. So this is the principle applied in Auchterlonie technique. So again, in Auchterlonie technique, this is a double passive immunodiffusion technique. So the gel does not contain an analyte. So we have here two wells. One well will be filled with the antibody. One well will be filled with the antigen. So for Auchterlonie, usually we are detecting the presence of the antigen. Therefore, for the antibody well, we place here known antibodies. Okay, so after placing the known antibodies and unknown antigen, we let these reactants diffuse through the medium. So at the point or at the zone of equivalence, there will be a formation of precipitin band. In Auchterlonie technique, we have three possible reactions. So we have first the line of identity, also known as the line of fusion. So in this technique, we have here three wells cut in our gel. So the antibody well will contain the specific or known antibodies. Antigen A will contain known antigen. Let's say, for example, antigen B will contain the patient sample. Now, we would like to know the identity of antigen B compared with the reaction of antigen A with the antibody. So after placing the antibody and the antigens, we will wait for the reaction. Okay, so after a while, there is a reaction. So here we have two precipitin bands or two precipitin lines. Okay, so the upper line is formed by the reaction between antigen A and the antibody, and the lower line is formed by the antigen B in reaction with the antibody. So we can see here that the two precipitin lines have joined together at one point. So we can assume that antigen A and antigen B react identically with the antibody. So since they have reacted the same or identically with the same antibody, it means to say that antigen A and antigen B are the same antigen. So let's say, for example, if the antibody well contains anti-HBs, that means to say antigen A is HBs antigen. And since they have the same reaction with antigen B's identity is now known. Okay, so antigen B is also HBs antigen. Next is the line of partial identity, also known as the line of partial intersection. So in our setup, we have here three wells. One well contains the specific or known antibody. Antigen A here will contain the specific or known antigen to our antibody. And then we have antigen B well. The antigen B well will contain the sample coming from the patient. Now, after placing the antigens and antibody, there will be a reaction. Okay? So in this reaction, we have two precipitin lines that are formed. However, there is a formation of spur line. Okay, so the spur line is found inside the red circle. Okay, so whenever there is a spur line formation, it suggests the presence of a cross-reacting antigen. Now, to know the presence of cross-reacting antigen, the spur line forms usually point towards the cross-reacting antigen. So in this reaction, antigen B is the cross-reacting antigen. That means to say, antigen B structure is similar to the epitopes found in the antigen A. However, they are not the same. Okay, so they are similar, but they are different antigens. That's why antigen B can still react with the antibody, although it is not the original antigen that has induced the production of this antibody. So it becomes a cross-reacting antigen. So the relationship of antigen A with antigen B is similar. Okay. Last is the line of non-identity, also known as the line of intersection. So again, we have here three wells cut in our gel. However, in this setup, the antibody well contains different antibody mixture. So we have here antibody 1 and antibody 2. And then we have two wells for our antigens. Let's say, for example, antigen A contains known antigens. Let's say antigen A is specific for antibody 1. And then we have here another well for our serum or for our patient sample. Okay, so the patient sample will be placed in antigen B well. Now, after some time, there will be precipitation. Okay, so in this reaction, we can find that two precipitin bands or two precipitin lines have intersected each other. Okay, so this means that antigens react independently with their respective antibody. So in our assumption, antigen A and antibody 1 are specific for one another. So in this reaction, therefore, antibody 2 is specific to antigen B, which is present in our patient sample. So since we have two reactions, it means to say that our antigen A and antigen B are not the same antigen. Next, we have the uses of Apter-Loney technique. Okay, so Apter-Loney technique can be used to identify fungal antigens, such as in cases of infections with Aspergillus, Blastomyces, Coccidioides, and Candida.
In addition, this has been a classic technique to detect antibodies to extractable nuclear antigens that occur in several autoimmune diseases. For other considerations in after-learning technique, we have the following. Okay, so first we have irregular patterns of precipitation which may occur from the following. Overfilling the wells, irregular hole punched in the well, and non-level incubation. So with these four techniques, we can have irregular patterns observed during after-loading technique. Okay, so the irregularities in the patterns will cause difficulties in reading of the result. Another concern is or are the factors which can affect the accuracy of results. Okay, so we have weak band intensity. Okay, so for weak band intensity, it may be due to drying out of the gels or inadequate time for diffusion. Okay. Next, we have presence of contaminants. So in the gel, there may be fungi or bacteria which may obscure the precipitation reaction. For any inquiries regarding this discussion, you may leave your questions in our group chat or open